So 2.6, I didn't say it was due today. We'll say it's the notes. You'll need to read the textbook on probably 3.6, 3.7 for Monday. So 3.6, 3.7 due on Monday. This is the first part of projectile motion. You've already done some labs, or a lab on that, where the ball was flying back and forth through the air. Don't have the stress ball, so I'll just use the skull here. A little breaker. Anyway, there's a couple of different scenarios when an object is traveling through the air in projectile motion. The first scenario might be when the launch height equals the stop height. It could be a situation where, like with my hands, where I'm throwing it back and forth and I catch it at the same height. Or you could launch it from the ground and then it hits the ground. Maybe if you were kicking a soccer ball or something like that. So the launch height, that's its initial y value, so that's why I have y naught. And its stop height, or its end height, or whatever you want to say, that's just y. And then you have two other scenarios. One where the initial height is lower than the final height. So maybe if you're throwing a ball up against a wall and then it gets stuck up against the wall. Or you throw it and it gets stuck up on the top of the roof of the building. Or maybe the ball is on top of the building and the gust of wind blows and it pushes it off. It'll be in projectile motion. Or if you climb up a ladder onto the roof and then you go and kick the ball off the roof, then its motion would look like that. What are some things that y'all notice about the path that an object travels when it's in projectile motion? It's always a parabola. It's always an arc. Yes. What are some things that we could say about an object in projectile motion? Do y'all know what projectile motion is? Like, what's that? Like a formal definition?
Is an object that moves in 2D under the
Okay, it's an object that moves in 2 dimensions, and it's under the influence of free fall. Is that what you said?
Gravity and nothing else.
That's right. It's basically free fall with a push in the horizontal direction. So remember, free fall, everything that we were doing in free fall, it was going just up or down. I mean, if something could something be in free fall when it was going up?
Yes.
Yeah.
How, Kevin?
Because the gravity is only acting on it.
Right, so if I were to throw this up and let it go, as soon as I release it, even though it's not technically falling just yet, it is in what we would consider free fall because the only force acting on it is gravity. The only acceleration is the acceleration due to gravity. And then at some point, obviously, it'd slow down, come to a complete stop, and then literally start falling. So, yeah, let's go ahead and put that down as far as a definition of projectile motion. Emily, what did you say?
I said is an object that moves in 2D under the influence of gravity and nothing else.
An object that moves in 2 dimensions. That's what this whole chapter has been about.
Under the influence of gravity.
Under the influence of love of the earth.
And nothing else.
I'll say only.
Okay, that's good.
What are some times in your daily life where you experience or have interactions with projectile motion? Sports. Throwing a ball, catching a ball,
Falling.
kicking a ball, falling off of a building, dropping the ball. Nancy, what did you say? Jumping. If you're jumping if you're jumping just straight up and down, then you're in free fall. But if you're running and jumping, like high jump, like leaping, like long jump,
Triple jump.
like the short jump. Yeah, they don't have a short jump. Oh, the triple jump. Okay. Yeah. Who can jump the shortest distance. Other situations for projectile motion? What if you fire a gun at an angle? Would that bullet be a projectile or
Yes.
projectile motion?
That'd be a small arc, but.
You gotta do that in everyday life, not every day. What were y'all saying? If you shot a bullet out of a gun?
If you did it like this, then it'd be like that. But if you do it like this,
Alright,
launch angle. It depends
You
on
can change the launch angle, but is it still projectile motion? As
Yeah.
soon as that bullet leaves the gun,
Yes.
then it's only under the influence of gravity, right? So you might, yeah, if you shoot it horizontally, it's gonna go like this. I didn't draw the picture, but I could. I mean, I'll draw it from right here. What if you're standing right there? You get a really long way. And you throw a ball, and you literally throw it completely horizontally, so it just goes like that. Is that projectile motion?
Yes.
Yeah, it is. I mean, it's projectile motion. It's not, it's at, what's the angle? What's the launch angle?
25.
Using launch height.
25.
What, launch, what's the launch angle? We would say 0, just because it's normally launch angle is either 0 up to 90 or down to negative 90. We don't really talk about a launch angle of negative, like 120 degrees, because that's really just like I'm shooting it this way. So launch angles are normally negative 90 up to positive 90. Yeah, my hands, when I go like this, wha-cha, when I was throwing, I gotta pick them up. Okay. Go ahead and experience projectile motion with the pencil and launch it to your neighbor there, okay? So, class activity.
I'll go higher, you go lower.
Okay.
I was like about to go high, I don't know why. Launch angles.
Coach, wait a minute. Nancy, Clark. Nancy, where is your paper?
You told me don't, you're gonna get out of it because.
I'll bring that lunch.
I do.
Okay, stop talking.
What do I do for you, Coach Lee?
I was getting these children to give me their paper, or there would not be a class officer.
Okay, can they get it to you at the end of class?
They can get it to me at lunch.
Okay.
Do you want my paper?
Yeah.
I got yours. Hey, Jasmine and Brooke, when class is over, come by my room.
Okay.
All right. Projectile motion activity is
Let me throw it.
ceased. I'm gonna try to show you something, which is actually pretty cool if I get it to work properly. All right. So I think we're all pretty good on this. Pretty good on launch angle. Yada yada yada. The next big idea that I'm going to show you for an object in projectile motion, or technically in any motion, that it's going to have, I think some of y'all saw this, at any given time, it's going to have a velocity. Actually, that is not very good. It's going to have a velocity, and that velocity is a vector. That's showing what's the direction that it's traveling at exactly that moment. And you could say that an object traveling in projectile motion has both a horizontal velocity and a vertical velocity, okay? So we're no longer dealing with just something just moving back and forth. Since it's moving through the air, okay, it has both a Vx and it has a Vy. Are y'all with me so far? It has a Vx, which is its horizontal velocity, and it has a Vy, which is its vertical velocity. Vx, Vy. Vx, Vy. And since those two things are vectors, if you were to add them together, then you would get their vector sum. This one is almost all Vx. It's got a little bit of Vx. Alright? Now here's the thing. They do not affect each other at all. The horizontal motion is its own thing, and the vertical motion is its own thing, and they don't mess with each other. Okay, they do not affect each other whatsoever. Okay, so to sort of kind of demonstrate that, I'm going to utilize this tool here, and I'm going to drop a ball, okay?
Oh, that's true.
At the same time, I'm going to shoot one out horizontally. So not at an angle. If I do it at an angle, then it'll mess up, okay? But I'm going to try to drop this one at the same time that this one goes sideways, okay? So when I do that, okay, as soon as I release them, they're both in what? Free fall, okay? And now this one happens to be in complete free fall with 0 velocity horizontally. This one will be in free fall, but it also is going to be, it's going to have a horizontal aspect of it, horizontal velocity. Okay? But what did I say? The horizontal velocity does not affect the vertical velocity. So in other words, these two balls should fall vertically at the same rate. Does that make sense? Even though this one is traveling horizontally. Does that make sense? So as a result, what we would expect to see, although not really, but we expect, is both of them are going to go like this. And hit the ground at the same time. You may need to stand up to watch it.
That one had out.
Yeah.
This one hit first. Did I have it at an angle?
You could use a meter stick and like put on the meter stick.
Alright, we'll try it again.
The meter stick.
But also the ball, the one on the, actually instead of getting hit, goes kind of off of the thing, so when the thing sticks out, it might hit it later.
We'll try again. 3, 2, 1.
That sounded pretty close.
So hit my hand. Where it went. Oh, here. This other one seems to be a little bit better, but it's a little bit rickety. Kevin, come on up here. So this one, it's so it's gonna go out like that. Okay. When I say now flip the switch, we need to kind of go over. All right. So this one, I'm gonna put it there, and so when he hits that, it's gonna send an electrical current through here, which will turn that magnet on, and it'll cause this to be pulled that way, and it'll pull it so fast that that one's just going to drop. At the same time, this one is going to shoot out if you got it if I did it properly. All right. Up, up, up.
Yeah, like something.
Not your fault. Go.
It fell off the foot.
It did fall. All right. Well, we're gonna do it one more time.
Just stack
Turn it
up
off.
those little board things, stack those up, and then you can sit on top
You
of
can
them.
like put this.
Oh, okay. You mean like this?
Yeah.
Okay. Gonna flip the switch.
Make it not crooked. It's crooked.
Look like that. All right.
It's okay.
No, no.
The actual thing on top is crooked.
Yeah, more or less.
Well, that
We
one
need to-
fell off.
Another person to like hold it.
Okay.
Yeah, yeah. Come on up here, Emily. I need that ball. The problem is that ball right there. I'll put that ball right on that groove. It's there we go. I'm gonna hold it steady.
I feel like it's gonna hit Emily.
I feel like it's a little, it's like, there's not enough room. Oh wait.
No?
Oh, so close. I think it fell before.
It was really close though.
Alright, we're gonna have to do this by hand. Alright, I got a little video here to show you. We'll leave this part to the professionals. Alright, y'all got a minute to talk here. Alright, back on. Here we go. Keep the lights there, Nancy.
They literally fly at the same time.
They bounce it.
There you go.
That's impressive.
So notice.
Make it slow the video down.
Yeah. But you see, this one, even though it goes sideways, now I ask you this, which ball travels farther?
The one that goes sideways.
Yeah, this one's horizontal velocity. But as soon as you release them, they're both going at 0. Right? They're both going at, I mean, they're both at free fall. They're both going vertically downward at the same time. So, and then they both bounce at the same time.
The one on the right side,
Yep.
like when it hits the ground, it goes up farther than the other one.
Just a touch. Yeah, it probably has. Yeah, it's probably got a little bit of spin on it. That's some good film right there. All right. Okay, lights, please, Kevin. All right, are you convinced? Horizontal velocity has nothing to do with vertical velocity?
Yeah.
All right, let's see if we can do this again. And I'm gonna need a longer table here. Come on in.
Hey, is this your son's? I found it on the ground.
Oh.
Not his. This is a regular McDonald's toy. Okay. All right. We're gonna need table space here, ladies. Ivan, can you man the camera?
Oh no.
It never rolls when it wants to. All right, you're gonna need to clear y'all's space here.
Are those expensive?
No, they're not that expensive. I'll put it sideways this time. Watch out, we're gonna be sending it down across the
Oh,
table
gotcha,
there.
that's neat.
Yep. All right, gather around here, folks. Maybe we should do this out in the hallway.
Maybe we should.
All right. Bring the camera there, Ivan. You're in charge of that one.
Oh gosh.
Also, we need another meter stick. Jasmine? All right, let's go.
Thank you.
No problem.
There we go. Are you filming? It's filming, right?
Yes.
Okay, good. You're the cameraman.
What they do.
Okay. All right. So what we're gonna do? It actually is. Just. Do you want to hold? Would you rather hold it? All right.
I got it.
Got it. So what we've got here is standard cart. It's just gonna be moving along. All right. When I hit this button right over here on the side, but the ball pops out, okay? So it's gonna be rolling along, okay? And then I'm gonna hit it. I'll try to do it in such a way that I don't speed up and slow down the part too much. The question is, when I hit that button for this to pop out, do you think the ball will land in front of the cart, in the cart, or behind the cart? I'm pushing the cart that way. Alright, vote with your feet. If you think that it's going to be behind the cart, you need to be over here in this area. If you think it's going to land in the cart, right there where Belle is. If you think it's going to land in front of the cart.
You go, Kevin.
Okay, Kevin, are you in middle or in front?
Middle.
Middle, he's middle ground. Alright. Jasmine, give it a push.
Mr. Goddard?
Yes.
Oh gosh.
Oh. You go, Kevin.
Alright, Kevin stands alone.
But does it depend on how
It's
the
recorded.
force pushes it up?
Yeah, can I push it faster?
Yeah, sure, push it faster there.
Oh, no, did not move faster.
That was the worst. Really fast. I know. I can do better. I can do better.
Anybody have an idea why the ball lands in?
Because it's going.
Vertical velocity.
Because the speed that
Vertical velocity has nothing to do with horizontal velocity.
that's
So think about it. The ball is in the cart the entire time. Okay.
It's already going that speed.
It's going 3 inches a second or whatever. It pops up, but guess what? The ball is doing. It's still moving along with the cart. Okay? And so therefore, it's just going 3 meters per second horizontally, 3 meters per second horizontally, 3 inches per second, whatever horizontally. And it's going to get popped right back inside. Alright? So, y'all have 6, y'all can split up into some teams. See if you can get it. The way you have to push it down, and then you hit it with the meter stick. Right there. That little button.
That's not fun at all.
Alright? So you'll have some fun.
It's pushed down, right?
You two ladies, and you ladies all come on over here and have pushers and
Oh, sure. Okay.
It's just right behind the battery.
I'm gonna do this right now.
Push it.
What am I supposed to do? Am I supposed to do
I don't make the camera. Y'all go ahead and swap out with one of these.
Oh!
We need a cart.
Anyway, that was great.
But you're the ball. The ball. The ball. Turn around. It's at the very end of the hallway. Go get the ball. Oh no.
You gotta be kidding me. I'm gonna hit this even harder.
It's harder than it looks. Did we get the ball? Did we get the ball?
Yes. It was like rolling. This machine costs money. You can really try to throw it.
Alright.
I'll throw it. Gently.
Maybe you need to prep yourself and be like at a ready spot, okay?
What's the red switch behind the?
Oh yeah, look, I was pressing it, it's just not popping out. It wasn't my fault.
What's the problem?
It doesn't pop out.
Did you push it
What-
out?
It's not, you have to push it down in.
Yeah, load it. It's a spring.
That's not working.
Alright, I'm expecting.
So I'm actually putting it
Alright, one at a time. Miranda, you're up first. Go ahead, Miranda, Jasmine, go.
I can't do it.
What?
Alright, we're gonna need a new person on the meter stick there. Alright. 3, 2, 1, go. Well, I was meaning for their team.
Wow. See, I actually did push it.
Hey, land.
Yeah.
Okay, I would just like to
Move the
say
camera at the wrong time.
harder than.
Too much ball game.
Yes.
You push it down?
Yeah.
Here, push it.
Alright, ball loaded.
Yeah.
Oh my gosh, you almost hit Kevin.
Oh, my bad.
Alright, here we go.
Can I go whenever?
Yeah, whenever.
Here, let me try to be
All right, let's give this one a shot.
Try it.
Is it loaded?
Everyone is like. Here, let me push it for you.
Hold on, Kevin. Try to hit the button when it's standing still, so you know what to do. You see, so you see what you have to do, right? All right.
You know how your first try
Like golf, like blue golf.
Yeah.
Oh.
Why did I go backwards?
It's because I pushed it.
It's really hard. Actually, believe it or not, what we have is there's a remote control that you do that hits it, but the remote control is broken. So that's my point now.
Okay, show off.
No, I tried this. We had a projection to do it.
All right. Anybody else want to give it a shot? Vindicate yourself.
Because then when you're successful, if you're good, and when you fail, then you can just hit it again.
Oh, whoa. Whoa. It's going for a ride.
You're like, see? So we were technically right for this.
We were right, yeah. With human error, we were correct.
There it is. Oh.
Again.
Did you give it a little tap? Maybe.
That's hard.
It's hard. Now, this is why. Yeah, these don't worry. They're built physics stuff. The thing is, I have a little remote control that you hit the remote control and it sends electrical signal to the spring to then pop. The problem is that part's broken. So actually, one of my computer science classes helped me yesterday. We took it all apart, tried to find out exactly what's wrong. We think we know what it is, but some bad connections. So, but that's why we're. All right, one more shot. Let's see if we're gonna. Who wants to verify this concept of physics with these strangely built custom toys?
It was in there.
Does anybody else want to have leadership?
I tried.
No, I'm trying to leadership. James.
All right, James is up. Yeah. All right. Benjay, are we loaded?
But see, my fingers
All right.
are still too
Brooke, you're up.
You might want to start.
Yeah, sure, you're up again.
Ready?
And it went in. Hooray! Clap, clap, clap. Coming back to you. All right, James, you got it. Oh. No, run away. Yes, question.
So if the cart's like already, if it's like already going at an angle, when it like gets hit, is the ball gonna land back in it, or is the ball gonna keep going like the direction? Because if it's going like this and the ball's going like this, it's
You mean like if it's coming down straight down the line here, like right along the column of all of these things, or you mean if it goes like
if
this?
it's going like at a diagonal.
James, push.
Is the ball in it while it's going a diagonal?
Yeah.
No.
Then the ball's got the same direction motion that the cart does.
But like if it's like still going at a diagonal when the ball goes up.
I think
Give me Eric, give her the car. Give her the car. Give her the car.
Is that what you're talking about? Look.
Hold on. Give her the car. Show us,
No,
Brooke.
I'm saying like if it's going like that, it's like going like this, and then like you hit the ball out as it goes up, but it's still going at the diagonal.
If you hit the
Like,
ball,
because it would be going like
Yeah,
straight,
like,
going
If you
straight.
stand that way, it's straight.
It's still going straight.
you're saying like, now are you saying
Straight to the way we're moving.
Wait, Brooke,
If
are
you-
saying if it curves like this?
Yeah.
So if it's going straight and it curves, will the ball curve with it?
only if here's the question: what makes it curve? Are you introducing a new force onto the cart to make it curve?
Or do you just mean if we were to get it and roll it this way and do the same thing again?
Because if it was
Oh, never mind. I understand now. I got it. It makes
It's straight, just not in parallel to the
Yeah, I
wall.
got it.
Well, there's a couple. I mean, it's a good question. Or another good question is also if the cart's rolling and then you hit the button and the ball starts flying through the air and then you kick the cart or the cart moves a little bit slightly, will the ball land in the cart? If you kick the cart while the ball's up in the air,
No.
no, it's
Because the change occurred when the ball.
you've changed the velocity of the cart. They no longer have a match for on their horizontal velocity. A similar thing is like here. I'll tell you somebody else. Stop the cart and at the same time hit the ball.
It's gonna go back. That's what we just did, yeah.
Oh, you
They
did.
were
So
behind it.
and if you stop the cart at the same time you hit the ball, the cart stops, but the ball is going to keep traveling. That's exactly what happens when you're in a car and the car stops and your body is still going. Yeah, and you go through it. Another interesting thing, I really think it would be cool if they made like an action movie. Here you go. All right, who wants to be the villain and I'll be the hero?
James.
All right.
He has a sword.
So Kevin is the villain, and we're both like on top of a train. Okay, so this could be like the train, and like he says, so we've got got our guns. I go for my guns, but he then says, hands up. And I say okay, and I'm like, all right, but I know physics, right? And so I only have one bullet, and so and we're both on a train going 60 miles an hour that way, and I shoot my gun straight up, and then I throw it down. Okay. Assuming no air resistance here, okay? And then I kind of like bring him back. I'm like, whoa, 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 everything's fine. He's really mad. I know he's gonna stop there in a second, all right? Okay, and I say, all right, what do you want? All right, stop. All put together. You gotta come one more step forward. Okay, and I say, all right, okay, I'll give you whatever you want. It's okay. It's everything I have is yours. And then just at that very moment, the bullet comes right back down.
That bullet was very slow.
Oh, that's so cool.
You see what I'm saying? Because the bullet was moving along at the same horizontal velocity as the train, and it's going to come back down at the same spot relative on the train as when I launched it, right? So I think that'd be a pretty cool. Or maybe if Bill Nye was like an action hero or something like that.
And you died.
So, all right, come on in here for one more demonstration activity here for us.
This was a lab where it said what to do from this lab. I would say I have anger issues. I knew I hit the button. I was like, why is it?
Oops. How do you do this?
Oh, yeah.
I feel so. Can I more specifically cover?
Are you using an expo marker as placeholder?
I am. It happens. Can we get that door for me? All right. I wanted to talk about some of the observations that y'all had yesterday. All right. When you launched it, the first thing I think was you said change the launch height. Is that right? So when you changed the launch height and you increased it, what happened to the distance that the ball traveled? Yeah, it increased. It went farther. Okay. Was that really a big surprise? Did I just hit the bullseye first time?
Yeah.
Wow, that's pretty good. Anyway, all right. So that probably wasn't a big surprise for you, right? Raising, lowering, if you're shooting from higher up. Okay. What was the next thing I wanted you to change? The initial speed. Okay. So if I have it set at 15 meters per second, it's going to go right there. And what happens if I increase the velocity in which it leaves the... It's going to go farther, yeah. Was that really a big surprise?
No.
Probably not. I mean, I can give it a launch angle here. And zoom out because we can't really see anything. I'll increase it even more. We should see... So there you go. All right, that wasn't very surprising. But I felt like the next one should have been surprising.
The angle.
The angle, yeah. So here we go, 15 degrees. I might dial it down a little bit here. Okay, so there's 15 degrees. And then I increase it to 25 degrees. What do y'all notice? Went farther and it went higher. Yeah, okay. So what I want you to do is say, okay, let's increase that even more, 35 degrees. More and more, right? Oh, but wait a second. This is where I told you because it gets really weird if you start launching from the same height. We go down to 0. So 25. I can get it up to 35. So the idea is the bigger the angle, the higher it's going to go, right? The farther it's going to go. Does that trend stay true?
No.
45, went a little bit farther, okay? I put it at 55, what's gonna happen?
It's gonna go to the same spot, pretty much.
Oh, that is 50. 55. Is it gonna go higher?
Yes.
It's
Yeah,
gonna
it's
go
gonna go higher,
But
but
it's-
it's, yeah.
35.
Oh, let's see if you're right. Yeah, it does go higher. But it also goes shorter, okay? What if I go to 65? Will it go higher?
Yes.
Yep. But it also goes shorter. In fact, we're looking at some pairs here. What was it? The 35 and the 55 degree angle both had the same range. But obviously they had different height. This one was higher. What was that other pair that we just did? 25 and 65. Same range, but this one was higher. Let's make a hypothesis. 10 degrees? What do you think that's going to match with?
25.
80.
25? 80?
I think it's 80.
I think it's 80 also.
Alright, so let's clear down here. Let's go.
You can't do.
I can't do any lower than that?
When you're on zero now.
Not at zero. You do it.
I didn't put it at 1.
What if I go here?
You can change that.
You can change.
No, they just don't have to let me.
You can change that.
You didn't change the
I
height.
can change the height, but it starts messing with things if you change the height. The optimum distance is no longer 45. Okay, but what about 45? How does that compare with all of those?
45 is a turning point.
45.
It is a turning point, turning 45 to 45. Yeah. If you're launching and catching at the same angle, 45 degrees is where you're going to get the farthest bang for your buck. You're going to be able to launch it the farthest, okay? If you shorten it, if you do anything less than 45 degrees, then it's gonna end up hitting shorter and it's gonna go lower. If you go any higher than 45 degrees, you'll get it to go higher, but not any farther, okay? When you look in your book, they'll go ahead and show that. So you can get the extreme case, right? What if you launched it at 0 degrees? Okay, what would that look like? What would 0 degrees look like?
Just straight.
Straight across?
Linear.
Yeah, okay. So if you do that, it's just gonna go, well, we can't shoot it at 0 degrees. If we shot it at 0 degrees from the ground,
So like it's level with the ground?
it's level with the ground, you shoot it at 0 degrees. It's, yeah, well, it's immediately, you're at the ground immediately. You're never even, I mean, yeah, it'll scoot forward and stuff like that, but, I mean, it's already on the ground, so it hits the ground. What if you shoot it at 90 degrees? Yeah, so that's kind of, if you shot it at 1 degree, okay, it would, horizontally just barely go like that, which would be the exact same ending position as if you shot it at 89 degrees. So you've got to go up and come back down. So what's the rule on these two numbers? Yeah, they have to add up to 90. There's a geometry word you learn, complementary. These pairs. Okay. So last bit, you still have your pieces of paper, right? Whenever I launch this, let's see if I can see where this is going to go. Let's talk about these things, the velocity vector. So how did y'all describe that velocity vector? What's the direction that velocity vector is going? The direction the ball is traveling?
But it changes, because at first it starts pointing up, so it means it has a positive velocity, and then it starts going down.
Okay, yeah, it starts off going up and to the right, and then at this point here, the velocity is completely horizontal, and then eventually starts going down and to the right. Okay, what about the magnitude?
It decreases as it moves, like up, and increases as it moves down.
It seems.
Definitely seems longer there, right?
Yeah.
Yeah, yes.
We like started getting shorter and then
The
longer.
closer it gets to the turning point, the shorter the magnitude is, and then once it starts going away from it, it starts increasing again.
Yeah, and the reason for that is because that is the total velocity vector of both its horizontal and its vertical component, okay? And when it's all the way up here at the top, it's all horizontal velocity. There's absolutely no vertical velocity. Right there, it's all horizontal. There's absolutely no vertical. Okay, but then after that, as it starts to accelerate downward, then you have a downward, horizontal and a downward, horizontal and downward. I want you all to come over here, or just look over here at this picture right above Vinjay's head. It's one of my favorite pictures, okay? Because it's projectile motion, and you've got the blue arrows. I'll step out of the way so you can see there. The blue arrows would show the horizontal velocity vector, and the red arrows would show the vertical velocity vector. Now, what do you notice about all those blue?
They stay the same.
Yeah, they're the same, okay? That's something about projectile motion, all right? Is there any acceleration in the x direction? No, because there's nothing pushing it or pulling it. There's absolutely no acceleration. So the horizontal velocity is always the same. All right, so repeat after me. Horizontal velocity is always the same.
Horizontal velocity is always the same.
All right, so that's a constant velocity situation. Just a distance equals rate times time. What do y'all notice about the red arrows?
They change.
They change, yeah. Why is the vertical velocity changing? Okay, but those are its velocity. It's not just, those aren't really its position, okay? Those are its velocity. Why does the velocity start off really large vertically, but then get lesser and lesser and lesser and then turn negative?
Because the acceleration is the gravity.
Because there's acceleration, right?
Because you're accelerating in the negative.
In the negative direction. So your velocity is going to go like a positive 10, then a positive 8, then a positive 6, then a positive 4, then a positive 2, then a 0 vertical velocity, then a negative 2, negative 4, negative 6, negative 8. Okay? Is there acceleration in the y direction? Yeah. What causes it? Gravity. Okay? So, follow me, Ivan. If you think about it, we've dealt with, in one dimension, we've dealt with two types of problems. We've dealt with constant velocity problems, where you're just traveling at a constant velocity in a set time, distance equals rate times time. We've also dealt with acceleration problems, okay? Projectile motion combines them both, okay? It's constant velocity in the horizontal direction, and it's free fall, that is acceleration due to gravity, in the y direction. Does that make sense? So when we do problems solving projectile motion, I'm gonna say, do all the stuff with the x over here, and do all the stuff with the y over here. And we'll find out that they also have the same time. Alright, today we talked about projectile motion, launch angles, vertical motion does not affect horizontal motion, and the drop sheet situation. Kill it.